Okay, so, well, I'm talking today about artificial intelligence. My presentation is about how to, what are the difference between artificial intelligence when you are learning and in theory and in a real world problem and in a business context. So, well, the content, this is the content of the presentation. First, I'm going to give you a little introduction about me and what's Equinox Lab. Then I'm going to talk about the difference between theory and application. Then building AI solutions in a business context. And I'm going to give you, at last, an example of one of our products. So, well, a little bit about me. I'm lead data scientist at Equinox. I've been here for like 3 years, leading the AI department. I'm a systems and computing engineer. I did my master's in data science at Glasgow University. And right now, I'm finishing a micromaster in statistics and data science from MITx. And I'm doing also my second master at Johns Hopkins University in artificial intelligence. So what's Equinox AI Lab? Well, it's the AI laboratory at Asesoftware. Asesoftware is our company. Asesoftware is a software development company. So its business core is to develop, to deliver software engineering services. But there are 3 other kind of services that we deliver through other labs. That's digital transformation, holistic design lab, and Equinox. So I'm going to focus on Equinox. And Equinox is basically the AI and data lab here at Asesoftware. We develop AI services. We also are the research and development department of the company, and that's it. So to begin, well, this first part, I'm going to talk about the difference between theory and application. So I want to start it with this data versus model. So when you are learning data science or artificial intelligence, you always have a model-centric approach. So what does that mean? That means that you are always focusing on building better models, more sophisticated models. You are always trying to tune the model to deliver the performance that you want. So, for example, if you are tackling classification problems or regression problems, when you are learning, you are focused on building the best model you can to tackle the problem. So this approach basically asks you how you can change the model to improve performance. And that's okay when you're learning and when you're experimenting, but there's another approach to data science problems and to artificial intelligence problems, and that's the data-centric approach. And this is not as fancy as building a very sophisticated and complex model, but the data-centric approach, it's what's changing industry around AI. So the data-centric approach asks you how you can improve your data in order to improve performance. So basically here you're focusing on data. How can I clean, or how can I have a better data set that's going to give me better performance no matter the model? Well, no matter the model. So this data-centric approach is what the industry is moving towards. And when you are building a solution around this approach, basically you are trying to build simpler models, but you are trying to build a complete solution that where you can encompass a process for building better data. So in this line of thought, you want data quality. And what do I put data quality versus data quantity? Because basically that's the data quantity when you are building models, having this model-centric approach, you want a lot of data. Why? Simply because complex tune again your model to work for that data. That's changing. But when you have a data-centric approach, basically you are from the beginning taking that problem into account. You are building a system that can change when data changes. So that's a main difference when you are building an AI project for a real world application. And following this line of thought, this second slide, it shows simplicity versus complexity. So that's the choice when you are selecting models. So what's a simple model? Well, I put a linear regression, a very well-known linear regression. And what's a complex model? Basically neural networks and its derivatives. So that picture is from a convolutional neural network that is used to detect objects in an image. So why I want or why I have this simplicity versus complexity? Because when you are learning data science, artificial intelligence, you always want to build this sophisticated stuff to maybe solve simpler problems. So I like very much this phrase, simplicity is the ultimate form of sophistication. Because it's not always about building very complex stuff. Simplicity gives you interpretability and computational efficiency. And what does that mean? That if you build a simple model for some task, you are going to be able to interpret why the model is predicting or doing what it does. Because if you have something very complex, like a neural network with many parameters, basically it's a black box. It's very difficult to interpret why the model is predicting what it predicts. And in some business contexts, you cannot have that. And for example, when you are an insurance company that you are classifying people to give some types of insurances, well, you want to interpret why your model is doing that. Because if you have a black box, then you cannot answer the question why this person or these people are classified this way. And in that business context, that's very important. And the other thing is that when you build simpler models, you have computational efficiency. So basically, you are reducing cost of computational power, of memory, of disk. Well, you are reducing many costs in computation. And I want to bring this graphic that shows the methods and algorithm usage. This is from State of ML and Data Science report from 2021 from Kaggle. Kaggle is I think is the biggest data science community that there is. And if you see the methods that are mostly or widely used are linear regression and logistic regression. These are by far the simplest models in machine learning, and are the ones that are most used. And if you see the convolutional neural networks are in 4th place. And are there not because just because they are by far the best algorithm to perform tasks for image recognition or object detection and so on. But I wanted to show you this because you always, in a business context, you always want to go for simplicity. If you solve a complex problem with simple models, then you're doing a very, very good job. Yeah, you are doing your model interpretable, you are saving costs, and basically you don't need to use a very sophisticated thing to accomplish the task. Then there is notebooks versus software components. So as data scientists, we all learn by notebooks. Notebooks are by far the best thing when you are learning data science. They allow fast experimentation. They are just perfect for learning. But they have a very big issue, and that's when you are used to build very bad notebooks, let's say it that way, that can lead to bad documentation and poor replicability. What do I mean by that? Basically, you can build notebooks that only you can understand. You can build functions that only you can understand. And if it's not in your machine, that's not replicable. Why? Because you have installed some libraries that only that specific code in your machine can compile. So that gives you poor replicability, and that's a very, very big issue when you're experimenting. Why? Because by definition, experimentation need to be replicable. Yeah, when you are performing scientific experiments, well, they need to be replicable. So notebooks are very good for learning, but you need to be careful how you use them when you are solving problems in a business context. You need to have very rigorous ways of documenting your notebooks, your code, and you need them to be replicable no matter the machine. Okay, and that's why the opposite of these unorganized notebooks are the fact of treating each step of the pipeline as a software component. And that means that the pipeline, when I say pipeline, I mean the whole data science or machine learning pipeline. For example, the data extraction process, then you have feature engineering, then you have training your machine learning model, then testing, and then deploying. Yeah. So if you treat each step as a software component, then you are going to have it will be easier to debug when mistakes occur, and they always occur. It will be easy to replicate, will be easier for deployment, and treating each step of the pipeline as a software component. It's the basis for machine learning ops. And software component can be, it's as simple as treating each step like a software component can be a function. So I treat my data preprocessing as a function that takes an input and it delivers an output that then the other components, like I don't know, the machine learning component takes. Okay, so if we treat these steps as software components, then we are solving many problems on poor replicability and bad documentation, because the definition of a software component is that it needs to work no matter the machine you're using. Okay, so if I build a function to pre-process all my data, as a software component, that function needs to work in other computers, basically. And okay, this is a very important thing when you are treating when you are in a business context where you need to deliver continuously new algorithms and new models, when you are tackling many AI problems. If you have unorganized notebooks, if you don't treat each step as a software component, then it's going to be very hard to keep up with the continuous delivery. Okay, then the second part is about building AI solution in business context. And here I wanted to use some quotes that we learned here applying AI for some projects, and as lessons that we learned, and developing these AI solutions. So the first one is that it's not just about data science. So yeah, it's funny to hear, but performing or developing AI, it's about the perfect mixture between design, data science, and software engineering. It's not just about building a model. That's just one part of everything. And when you are building an AI solution, first of all, you need this design part encompasses many things. This design part encompasses business knowledge, it encompasses user experience, user interface design, interaction design, and well, some other stuff. But that design part is very important because the designers are the ones that are performing research on the users and on the business processes. They are the ones that have the knowledge, the business knowledge, and at the end they know the specific pain points in a business process that, or where AI can deliver a unique value. So, for example, if I have a process, the designers are the ones that are going to tackle a business problem. That business problem, the context is a process of, I don't know, manufacturing. And they are the ones that have to use the knowledge of the researches that they perform with users, the business knowledge that they have about the context, and the knowledge that they have about data science, how to apply data science. They don't have to know how it works, how a linear regression works, or they don't have to know what's a linear regression, but they have to know what AI is capable of in order to spot opportunities, to spot pain points in the process that only AI can bring a unique value. And I say a unique value because not everything needs to be AI. Okay, no, it's a very misconception that we need to put AI in everything, and that's not the case. The designers need to know how I can use artificial intelligence capabilities that brings me in this process a unique value that no other transactional system or IT system brings. And that's a very important thing. It's because it's the beginning of the whole project, of a whole solution. Then that's where this specific pain point where artificial intelligence can bring some value, it's translated to a data problem. And that's where data scientists come. They take this data problem and solve it through algorithms, through statistics, through machine learning, I don't know. But there is a last part that is how I can deliver the solution. So yeah, I solved my data problem. I built the best model that I could, and what now? So we need to deliver that solution somehow. The ones that are the best suited for deciding how to deliver are the designers, are the ones that know the business context, are the ones that know that X prediction model you need to deliver in through this interface because it helps the user experience. Those are the ones that have that decision power in the design of the solution. And after that, then it comes all the software engineering part, because after all, everything is about software components. When you are building AI, you are embedding your model in an IT system. So you need to know the architecture of the IT system. How can I better approach to this architecture with my restrictions, the model restrictions, the data restrictions. So all this architecture, this software architecture, it's very, very important to build an efficient and a usable solution. And that's where software engineering comes. So I have this slide that's our motto in Equinox, and that's that we care about technology, care about humans, and we care about the balance between them. Because for us, building AI is about constructing this this relation between humans and machines, and that perfect relation needs to be constructed through design, through data science, and through software engineering. This second quote says, it's not like building a conventional IT system. And why do I have that? Because a conventional IT system is a transactional system, basically. And I have an example of a transactional system. The best example is a bank, an IT system for a bank. So where that's a system where you can basically perform transactions. You can pay stuff, you can receive money. And there are AI systems. And the best example is Netflix. So Netflix understands you, gives you recommendations, and it basically tunes the interface of the platform to suit you. So what's the main difference between these two systems? A transactional system, when you're building a transactional system, you are not allowed to fail. A transactional system cannot fail, never. A bank cannot, a system of a bank cannot fail, never, never, never. So yeah, basically when you pay something, you expect that transaction to always work. And that's a very different thing when you are building an AI system, because you don't expect Netflix to always give you the best recommendation. You don't expect Netflix to always understand what you want to see. So that's a very important thing to take into account, because you need to define the scope of the AI system, and you need to take into account the higher amount of uncertainty that you are dealing with when you are building an AI system. So first of all, you need to plan for experimentation. You always plan for experimentation. Why? Because when you're building, if you are building a recommendation system, you cannot just say, I'm going to build the data extraction process, then the machine learning model, and then deploy. Because you need to plan for experimentation. Something can go wrong in the way you are dealing with the problem, in the way you are building the model, in the way you are deploying the model, because you are dealing with uncertainty. And that's why you need to plan for experimentation. Always take into account experimentation. You also need to define scope and expectations. So as I told you before, for an IT system is easy. It works or it works. It's nothing left to chance. But for a recommendation system, it's not always going to work. So you need to define expectations. You need to define your goal. So I'm going to build a recommendation system that is going to work 80% of time. So I am aiming basically for, I don't know, 80% of accuracy. Then you can't just have plan A. You need to have plan A, plan B, plan C, plan D, because it's very difficult to have it right the first time. And when you are building AI, many times you find that after building the model, maybe you are tackling the problem just not right. So maybe you are not taking some data into account. Maybe you are just building or trying to solve a recommendation problem some way that just don't work for the business context. So you cannot just say, I'm going to build this component, and this component, and that's it. I'm going to have 3 months to build this, and that's it. No, you need to have plan A, plan B, and plan C, always. So yeah, I'm going to build it this way. I'm going to use this model, but if that does not work, I'm going to iterate this way, or I'm going to, in parallel, I'm going to try other models or other approaches. And finally, you need to receive fast feedback. So that's very important, because and it's not just fast, it's fast feedback in every step of the process. So you need to receive fast feedback from your models. It's my model working? It's my data okay? I'm framing the problem okay? But you also need to receive fast feedback. If it's your way of delivering the solution the right way for the users. Is the interaction that you designed for your AI system it's okay with your users? It's usable. It's efficient. So in every part of the process of building an AI system, in the design part, in the data science part, in the software engineering part, you need to receive fast feedback. That's going to change many things along the way. So it's important for you to take into account. This last part is about using AI services, because there is a lot of hype around using auto ML tools, or just stuff that makes your life easier. And there's a lot of hype around these ML tools, auto ML tools. But basically, right now at 2022, we don't have that. We don't have something that can help us for building automatic artificial intelligence. Yeah, or that can help us in a usable way. So I bring you this graphic from the same report of Kaggle of the enterprise machine learning product usage. So basically, here is plotted what are the tools that data scientists use for building machine learning products, or machine learning solutions, or data science solutions. And the first one, by far, is none. So it's a lie that you need to start learning from Google AutoML or Amazon SageMaker, or I don't know, all these AI products. Because in practice, many people just don't use them. They are not at the level that they should be to be called auto machine learning tools. So yeah, basically nothing today is going to make your life simpler when you are data scientist, and word scientist is in there. You need to have the knowledge of the algorithms, of the things that you're using and how to use them to apply them to specific data problems. That's our job, basically. So nothing's going to replace that. If you having the knowledge to perform these algorithms is never going to be compared to having a good Amazon SageMaker tool or auto machine learning tool for now. So basically what I want to show in this slide is that, well, first of all the hype about these tools is very misleading, and second, well, basically you can build enterprise applications or AI applications using open source software. This, and I want to clarify that this slide, this graphic is about AI services. Okay, so it's not infrastructure, because everyone is putting their infrastructure, their machine learning models in Amazon or Google or Microsoft infrastructure, but it's different to use their tools to design artificial intelligence, to use their tools to simply compute your design. So yeah, and finally, this last part is about a product that we have here. There is Numerate, where you can see all this stuff that I'm telling you. So before I talk about Numerate and what's the product, and well, we go deeper into that, I wanted to tell you how was the story of Numerate. So it all started with a business problem for one of our clients. It was a retail company, and basically the problem it was in the way they were doing inventory. So they have some processes to store their products. For example, a shipment of steel bars comes into the store. They perform the inventory and they store it somewhere. And after some time, they need to move that into another store, and that's the idea. So the problem here was that inventory, basically it resumes to counting the steel bars that were entering the store, and that process was done by a human. And these images are some of the things that the packages of steel bars that they need to count. And as you can see, it's very tedious and time expensive to count how many bars are in these packages. The process was was performed by a human that for a package of 300 and something bars, the human counting those bars took like 10 minutes for one package. And that package is the smallest one. The bigger package was like thousands of bars, like 2,000 of bars. So you can imagine how many time was wasted counting these bars when they enter, when they go out of the store. So we approach this problem, of course, with computer vision. So basically, we want to answer the question: can we build a model that counts a lot of objects? Because 3 years ago, there were many models to count objects, many, but they were not designed to count such high amount of density of objects in an image. So we couldn't use those models and plug them in our solution because they were not working all right. So we started to do some research and some experiments, and finally we arrived to this first model. This first model was a combination of 3 algorithms. First, a convolutional neural network, then an outlier detection, and then a clustering algorithm. And as you can see, this is a very complicated solution. This is the convolutional neural network was not a simple convolutional neural network, but very complex convolutional neural network. It was the architecture was RetinaNet, and at the time, RetinaNet was something very sophisticated. And as you can see, for counting the objects in one image, we had a very complex solution. But it worked fine for some time, and we developed our first MVP. So basically, our first MVP was just a web service where you put your image, and it returned this image with the bars highlighted and the counting, the results of the counting. But we made a lot of mistakes, and we had a lot of weaknesses. Why? Because we were not applying anything of what I just told you. So basically, we had a very complicated solution. We had unorganized code everywhere. So the first time we developed this stuff, we did it through a lot of notebooks and a lot of unorganized notebooks. We had poor documentation, and the solution we built had no user experience and no software engineering. So we took into account everything that I've just told you, and we built a version 1.0. So basically, the 3 fronts at Equinox developed this first version. And in the data science part, we built a simpler model. So from 15 seconds that the model took to count the objects in one image, so 15 seconds of inference, we accomplished 1 second after building a simpler model. We also built every step of the process as software components, and that allowed us to experiment faster and to build newer models faster, because for each type of object, you need to build a model. So this is the model that counts steel bars, this is the model that counts tubes, and so on. But at the beginning, we were just counting steel bars because the experimentation and the deployment of a model was very, very hard. So after building software components for each step, we were able to build faster models, and not just faster models, but we create new models faster. And in the design part, where we took a step back, we deployed UX research to design the solution. So basically, some designers took the time to know the business context, to know the users that were going to use the solution. And we found that the best way to deliver the solution was through an app that should respect all the UX design principles and have a well-defined brand. So basically, we were going to deliver our accounting solution to an app. And finally, the software engineering, we had this software engineering part to build an architecture that allowed us to decouple the AI service from the app. So basically, when you are using Numerate and you are, I don't know, you are looking for your history or your count, your counting history, or I don't know, you're using the app, the moment you press count, you are calling the AI service from other place. That's the cloud. The AI service runs on the cloud for software requirements that we needed at that time. So a very well-defined architecture allowed us to build a faster solution and a more efficient solution, taking into account the other restrictions that we had. And this is Numerate today. Okay, so basically we had a very high leap from the beginning to building this app that you see in the video. And this is just to so you can see the look and feel of the app. It respects all the user and the user experience design principles. It basically, we have now a very precise target market, and it how it works is very, very simple. Basically, you just select the object you want to count. Basically, you select the model behind cartoons, you take or upload your picture and then you use a filter if you don't want to count all the objects in an image. Yeah, because we saw that when the final users were taking pictures of not just one package of bars, but many packages in one picture, but they just wanted to know the count for one package. So we developed that filter, and yeah, basically you can store your counts. And a very cool thing about the app or the solution is that you can remove or add text. So basically you can use the app to tell the model where did it wrong. where the model failed. Okay, so that function allow us to build better data sets for future models. So it's a very it's a very cool way of having a data quality procedure and of embedding the users in our data quality procedure. So yeah, we started with a rough first version of our solution, and after applying everything that I've just told you, after using embedding design, software engineering, data science, good practices in data science, we built this app that right now is on the App Store, and we are in a kind of a beta test version, because we want to build a version where you can when you can use the app for 7 days, like a trial. And we are just developing that for, I don't know, the next month. But right now is you first have to pay on the platform, and then you can use the app. But yeah, this is an example of how these good practices and this all the stuff that I've told you can be used in a real world application. So, well, that's Numerate. With that, I conclude my presentation. Thank you very much. These are our a link to our social networks and our website if you want to connect. And that's it. Thank you very much for having me. So I think right now we can, if there's any questions, we can answer them. There are some comments. We can look into that.
I have a question myself. How long does this process usually take? For Enumerate, for example, like specifically, how long did the IA like take to develop, and from like the initial like idea generation all the way to actually releasing the app, the finalized version after having fixed out all of the errors that you had with unorganized code and everything?
Well, that depends. If you already from the beginning do the right stuff, it shouldn't take that long, because the first time we developed that first model and that first MVP, it took some months, I think like 3 months to develop that first MVP. That was a very rough idea of what we wanted. But after that, right now we can add new functionalities, new models, and basically new stuff to the app, because we have a very organized process to do it. So it's hard to answer. It shouldn't take long if you do the right stuff from the beginning. And what takes the most time is to test your idea. So it's not building a model. It's to test if this product is going to work. So you test it with clients to go and retrieve data. That's the most where the hard work needs to be done. But I would say that no more than this app could be, from the beginning to the end, could have been done in no more than 6 months.
My second question was, if you have to give like a couple of pieces of advice, like a general concept to someone who's starting off now, maybe they're university or they recently graduated and are thinking of pursuing a career in artificial intelligence, what would you advise them? Like, where do you start when you literally have no idea where to go first?
Okay, so So I would say that if you want a career in AI, you need to have good basis in all data science. So basically, you start learning probability, statistics, data visualization, and after that, you can go deeper into the fancy stuff like machine learning and neural networks, deep learning, and all that stuff. And because it's very important to understand that artificial intelligence is not machine learning. So that's like my main advice. So you can build predictive models with simple statistics that work better than machine learning models. You can build better solutions with just data visualization concepts and probability that with machine learning. So my advice is to try to be holistic in how you approach artificial intelligence, because it's not just machine learning and deep learning.
Okay, great. Thank you so much. I think we have like 1-2 minutes. If anyone has one last minute question, if not, no? Okay, so thank you so much for coming, everyone. And thank you so much, Alejandro, for taking the time to talk to us and tell us about this amazing project and the world of artificial intelligence.
Okay, thank you too for the invitation. Okay, bye.
Bye, everyone. Thank you for coming.
Thank you.